Okay, so we're going to start out here for the second semester with a little bit of review of one of the most powerful concepts in math. Addition. No. Talk about ratios. What is a ratio? Well, a ratio is just a comparison between two numbers. For example, we could do a ratio of students wearing hats to students not wearing hats. And here we have 1, 2, 3, 4, 5, 6, 7 students wearing hats. 1, 2, 3, 4, 5, 6 students not wearing hats. So we get a 7 to 6 ratio. Now I could write it like that as a fraction, a 7 over 6. I could write it with a colon, 7 to 6 like that. Or I could even write it with the word 2 in there, 7 to 6. And there are a couple other ways that we could express it, but they all mean the same thing. We have 7 of one thing compared to 6 of the other. Now, I often prefer to write it as a fraction like this, because as a fraction, or in that form, we can do a lot of the same things with it we do with a fraction. Let's say we look at the ratio of students in here that had credit for last semester to the ratio of students in here who didn't have previous credit for last semester. So 2 to 12. As a fraction, I can reduce that. Both 2 and 12 can be divided by 2 to give me a 1 to 6 ratio. It's the same ratio, it's just in a simpler form. So that's saying 1 to 6, or 1 out of every 6 students in here had previous credit. Now in this form, I could still do the same thing, or any of the other forms, I could still do the same thing. We're just not as familiar with it as we are in fractions. I would still be able to divide each of those by 2 to get a 1 to 6 ratio. Let's take a look at these tables here. Let's do a length to width ratio. Those are 6-foot tables, so they're 72 inches long, and they're 18 inches wide. Now the inches cancel out. 72 and 18 can both be divided by 18. That gives me 4 and 1. So there's a 4 to 1 length to width ratio. Now a couple of things I want to point out there. One is, one of the first differences between a ratio and a fraction is, if that were really just a fraction, I'd just reduce that to 4 and that would be it. A ratio always is a comparison between two numbers. So even though it reduces like that, I cannot get rid of the 1. It has to stay as a fraction, or the comparison of two numbers. The second is, there are no units in that. That is 4 to 1. And it doesn't matter what the units are. It's 4 units of length for every 1 unit of width. I could be looking at that table, and it could be 4 inches of length for every 1 inch of width. It could be 4 centimeters of length for every 1 centimeter of width. It could be 4 feet of length for every 1 foot. Whatever unit you use to measure the length, use that same unit of width. And the length is 4 times the width, whatever it is. You'll also notice here that in every ratio I did, the name is the same in both numbers. This is comparing inches to inches. This is comparing students to students. And the same up here, students to students. That is another requirement of a ratio, as it compares two things with the same label, or the same name. I could run into something like this, 2 feet to 18 inches. Is that a ratio? No, it's not, because they have different labels or different names. I can change the names, however, to make it a ratio, because 2 feet can be converted into 24 inches. So now it's 24 inches to 18 inches. And the inches can cancel out. I have 24 to 18. Both of those can be reduced by 6 to give me a 4 to 3 ratio. Now here's a second difference between fractions and ratios. We said the 4 to 1 has to stay as 4 over 1. We can't make it just 4. Here, 4 over 3 If this were a fraction, we would make it a mixed number, 1 1/3. But it's not a fraction, it's a ratio. It's in fractional form, but it's still a ratio. And so a ratio is always a comparison between two numbers. So we have to leave it as two numbers, 4/3. So we've said that a ratio must compare two things with the same name. What if we have two things that don't have the same name and we can't change them? For example, let's say we send Drew on a road trip. And Drew manages to go nowhere. Let's say we send Drew 400 miles. And it takes him 7 hours to get there. Now, there is no way to convert miles into hours or hours into miles. This cannot be turned into a ratio. It is what we call a rate. The first major difference between a rate and a ratio is a ratio compares two numbers with the same label or same name, and a rate compares two numbers with different names. Now, because of that, a ratio doesn't need units. A rate must have units in it. The second big difference between a rate and a ratio is a ratio, we'd reduce it as far as we could, but it's okay to leave it as 4:3 or 1:6. A rate is almost always reduced to what we call a unit rate. What that means is we divide it down until the denominator is 1. 1 hour in this case, 1 unit. How do we change 7 into 1? Well, we would just divide by 7. We would divide by the denominator to reduce it. 7 hours divided by 7 is 1. 400 miles divided by 7 is 57.142857143 approximately miles. Correct? So now it's a unit rate. The denominator is 1 unit. Now usually we won't even leave it like that. We'll rewrite it. I'm going to round this to 57.14 miles per hour. We rewrite it like that so that the fraction in the numbers is kind of hidden, and the fraction is disguised, kind of slipped into the units like that, miles per hour. In fact, sometimes we even go one step further and we just say mph. And when we see it that way, the appearance of the fraction is completely and totally gone. It's hidden. But we have to remember mph is miles per hour, and it is a fraction. Technically, it looks like this. So let's say that on this trip, Drew got 28 mpg. What does mpg stand for? Miles per gallon. So whenever we see that 28 mpg, what we need to think is this: 28 miles per 1 gallon. Because this is the form we need it in to do any calculations with it. We have to put it in that ratio or rate form, fractional form. Any questions? So for rates, there are all sorts of rates out there. We just saw miles per hour, miles per gallon, a lot of other rates that you might run into. Probably the most common one and most important one in your lives right now might look like this. That's a rate. Your wage is $11 per 1 hour. You can look at consumptions. You can look at all sorts of things. You can look at time to do a task. For example, let's say you're doing texturing the sheetrock in a room. You might figure 20 minutes per room or something like that is your standard time consumption. If you're doing estimating for a house, you might do $32 per foot of exterior wall is your estimate for the cost of putting up the exterior wall. Little things like that. Yeah, a lot of times you do by square foot. Like roofing, I'll charge between $180 and $200 per square of roofing. That's a square is a 10 by 10 or 100 square foot. So let's look at some more rates. There's all sorts of rates out there. Or not rates, let's look at ratios, sorry. We've all sorts of rates out there and you see them every day. The ratios are around you too, they're just not quite as obvious all the time. Let's maybe look at, let's do this. Any guesses? A gear? Good guess. So we have two gears meshing together. We're going to talk about a gear ratio. Now a gear ratio looks at the number of teeth. How many teeth are in this gear here? There's 15 teeth, right? How many teeth are in this one? 9. So we got 15 teeth and 9 teeth. A gear ratio is the number of teeth in the driven gear to the number of teeth in the driving gear. So, how do we know which one's driven and which one's driving? Well, we need more information. So we're going to go back to my impressive artistic talents. Pretend that's a little electric motor connected to the shaft of that gear. If I separate the gears, one of them is going to stop and one's going to keep turning. Which one's going to stop? The 9. That is the driven gear. It is being forced to turn by the other gear, driven by the other gear. That's my driven gear. So it has 9 teeth. The driving gear is the one that's connected to the power source. It'll keep turning if we separate them. That is the 15. So we have a 9 to 15 gear ratio, and of course I can reduce both of those by 3, giving me a 3 to 5 gear ratio. Any questions?
That's always how it is. It's always the driver over driving.
Driven over driving. Yep. Driven over the driver. Whichever one's closest to the power goes on bottom. If you're looking at pulleys, there are no teeth. The pulleys have no teeth, so we just measure their diameter. We compare the diameters. On a gear, the number of teeth is really just a way of making the circumference because the teeth have to be spaced exactly the same. So the number of teeth will tell you the size of the gear. So let's say we have a 10-inch pulley and a 4-inch pulley. What do we need to know? We need to know which one's the driven and which one's the driving. Very good. So if I put that little electric motor in there, or what simulates an electric motor, what does that tell us? Which one goes on top? The 4. And then the 10-inch on bottom. And then, of course, we're reduced to what? 2 to 5 pulley ratio. Those ratios, the gear ratios and the pulley ratios, both have the same relationship. They describe a lot of things. That is the ratio of the RPMs. 2 to 5 ratio means that the big pulley will turn twice for every 5 turns of the little pulley. Or the big gear up here, 3 to 5, the big gear turns 3 times for every 5 turns of the little pulley. It's a power ratio. The power in the small pulley will be 5 times, or 5 units of power in the smaller for every 2 units of power in the larger. There's a power ratio there. So anyway, anybody, let's do something else. Let's look at, since we're doing mechanical applications, we'll do this one. Anybody want to guess? Pistons, very good. We're looking at a compression ratio. Actually, it's the same cylinder, just 2 different points in time. Compression ratio is the expanded volume compared to the compressed volume. So let's say that this here is 32 cubic centimeters. This is 256 cubic centimeters. Which one's the expanded volume? 256. Compressed? 32. And of course, the cubic centimeters divide out. 256 and 32 both can be divided by 32. Give me an 8-to-1 compression ratio. What do you think? Good stuff? Let's look at something more specific to construction. Yes, roof. Anybody here know the difference between a slope and a pitch? I kind of figured that's how it'd go. Well, slope is always given as out of 12, but there's also a difference in where they come from as well. So let's look at the span of a roof with a given height. The pitch is always the height over the span. That is the technical definition of pitch. So let's say this roof has a 24-foot span and 6 feet of height. So its pitch is 6 feet over 24 feet, which reduces to a 1 in 4, or a 1/4 pitch. Now, pitch was used whenever you use a conventional ridge beam and rafter system, because the pitch tells you how high to set that ridge beam. Let's say here's our walls. If I want to know how high to set the top of this ridge beam here, the height of that ridge beam above the walls is the pitch times the span. So let's say that we have a span here of 36 feet. 36 times 1/4, that has to be 9 feet. The top of the ridge beam is 9 feet above the top of the wall. So that's what the pitch was for. It described the height of the ridge beam. Now, the truss didn't necessarily have to be a common truss like that. It could have been shaped like this. As long as that height was 6 and the span was 24 in this case, it's still going to have a 1/4 pitch. It doesn't matter whether that ridge beam is centered or not. It's just the height of the ridge beam above the top of the wall compared to the span. Slope, however, is rise over run, and it's always out of 12. The rise here, of course, is the height of 6 feet. The run is not 24, though. The run is half the 24 would be 12 feet. Now we're making the assumption that this is the same slope on both sides. So it's a 6 out of 12. I know that reduces to 1/2, but as we mentioned earlier, the slope is always given out of 12. There's a reason why I chose the 24. We'll look at how you can convert it into over 12 later. This roof down here is going to have 2 different slopes. Obviously, this side is steeper than this side. They both have the same height or the same rise, just a different run. Another construction application is grade. Can anybody describe to me what grade is? What's that? It has to do with the elevation of the ground. Very good. It actually is the slope of the ground. Um, so let's say we've got a piece of land here that in 200 feet, it rises 28 feet. The grade is technically rise per 100 feet. So we have a rise of 28 feet and a run of 200 feet. What I have to do is I have to convert that 200 into 100, right? So I'm going to just divide by 2. So that's going to be 28 out of 100. Or what we call, or not 28 out of 100, 14 out of 100. Or what we call a 14%. Remember, percent means out of 100. So that's a 14% grade. Is that steep? It's pretty steep. You guys familiar with Highway 8 over by St. Croix Falls? Where they give you the big warning sign, you know, trucks downshift and all that. Anybody know what the grade is there?
Stupid, because trying to tow a Honda on that with my truck is
That's an 8% grade. 8%. Yeah. Yeah, trying to accelerate going up there is really silly. The speed limit used to go up towards almost at the bottom of the hill, which is a little better, but they've moved it way up. What I don't like is they put a roundabout right in the middle of Highway 8 when it's like 45 miles an hour. It's like, you're supposed to go around the roundabout at 45 miles an hour? I can do it at 60, just so you know. We don't talk about that much, though. So anyway, that's basically our ratios. So the next step then with those ratios is to go on to a proportion. So let's say we have that gear ratio that's going to be a 3 to 5 gear ratio. 3 teeth in the driven gear for every 5 teeth in the driving gear. So let's say I have a motor that has a gear on it with 35 teeth. How many teeth do I have to have on the other gear to mesh with that to make this ratio? Well, does the 35 compare with the 3 or the 5? It's on the motor. So is that the driven or the driving? Driving. So that goes on bottom. How do I find this number up here? Yeah, we did our percents last semester, which were basically a proportion. We cross, multiply, and divide. 3 times 35 is 105, and we divide by 5. You get 21. So that other gear has to have 21 teeth in it to conserve that gear ratio of 3 to 5. Now, another common ratio that you'll run into is a debt to income ratio. Most banks, most lending institutions go off a 1 to 3 debt to income ratio. They don't want to give you a loan that's going to push you above that. So let's take a look at this for you guys. When you get out of school and get that first good job working construction, how much do you expect to be making? Honestly, now, how much do you expect to be making a year? What's that? You're going to make $11 an hour? Hopefully your pay goes up a little bit once you graduate. What's that? Yeah, 30 to 30, between 28 to 33 is about average for you guys. So 30,000 is a pretty good estimate. So that's per month. 30,000 comes out to be about $2,500 per month. That is your income. Vehicle loan. How much do you expect to be spending on a vehicle loan per month?
$100.
$100 a month. Okay, most people drive a little bit better cars than you do. $100 is a good number, but most people pay $100 a week. Yeah. Well, put it this way: how expensive of a vehicle do you plan on owning? Put it that way. 10,000, 15,000, $200, 200,000. I did notice there's a Lamborghini up at Don Johnson's up here that they have for like 170,000 right now. It's the only car I know of in the area that's that much. So anyway, you want to say a $10,000 car?
Yeah.
Okay, so a $10,000 car is about $200 a month. You plan on owning a home or renting a home? Own? How much would you want to spend on a house if you were going to buy a house? Okay, we do want one with like insulated walls. And I know you can't do double layer cardboard. So anyway, $100,000 house, $120,000. $100,000 house would be about $525 a month for your house payment. Credit cards?
$25 a month,
Make minimum payment. So you'll take that 30-year plan to pay off your credit cards? Let's go 25 a month. What the heck? We'll keep Drew happy. Assuming you don't have any student loans or anything that you're paying off, let's add these up here. That's $750. So a 1 to 3 debt to income ratio. Let's plug in our $2,500 for income. If we cross multiply and divide there, what do we get? That is $833 pretty much, right? So what that is saying is, with a $2,500 a month income, we are allowed up to $833 worth of debt payments. So you can see $200 car, $525 house, $25 on credit cards, that's $750. We're already pushing it. Now, if you have student loans, and you have student loans that are $200 a month, and that's not unusual. Some of those are $300-400 a month that you're paying off. Put that in here instead of a house, and put in $300 a month for a student loan, and you're looking at $525 here. And your credit card payment's probably going to be more than $25 a month. But now you're looking at that. You only have $300 a month off of that $833 to make a house payment. Chances of you buying a house while you're paying off your student loans are pretty slim, unless your income goes up. And that's a trap a lot of people step into out of college, is if they're making a car payment and making credit card payments and on top of student loans, they don't have a whole lot of credit left for purchasing a home. Now the other side of that is, let's say you don't have a car payment. So now you do have $400 and some freed up to buy a house, and you find a house that fits your budget. Well, now what happens when your car craps out? So I mean, you have no credit. You have no credit left to purchase a car. So that 1 in 3 debt to income ratio is not there as something you should stay at. It's a limit. It is a cap. You should always try to look at your income and stay below that enough so that if something does happen, you have available credit. I mean, you heard about the big mortgage collapse about 9 or 10 years ago. Part of the problem there was a big push by some of the federal agencies that regulate lending to change that from a 1 in 3 ratio to a 2 in 5 ratio. So from 33% to 40%. So what that would have done with your $2,500 a month income would have meant now you could afford $1,000 a month in debt. That's $167 a month more. Do you think you could really afford that much more? No, that was just they changed their lending standard. So people were getting more debt. Why is it only 1/3 instead of more? Well, because approximately 1/3 of your income goes towards taxes, and the other 1/3 of your income goes towards bills like electricity, groceries, stuff like that. So you start putting that $1,000 a month in there instead of $833. Now you don't have enough to pay your electricity and all your other stuff. Any questions? For right now, let's give you some homework to work on for the first hour, and we'll come back and we'll talk about this more in our second hour. In your textbook, on page 154, it is exercise 4-2, 1 through 31, the odds. This is actually just talking about ratios, writing ratios and simplifying them. I'll give you guys 7 or 8 minutes to work on those, and we'll take our break, and we'll talk a little bit more about proportions.